Next one. This problem always makes me laugh. The health of employees is monitored by periodically weighing them in. Wouldn't that be fun? A lot of times we discuss this in class. What type of job do you think might require employees to weigh in? And typically we come up with maybe law enforcement, maybe military. I have a friend who's a flight attendant, and she said they used to have to weigh in. And the reason was in terms of the plane being able to fit through a window if you needed to make an emergency landing and get out of the plane quickly. They don't require that anymore. So we have the health of these employees. They're getting weighed in. We have a sample of 54 employees, and they have a mean weight of 183.9. Assuming the standard deviation is 21.2, use a 0.10 significance level to test the claim that the population mean is less than 200. So we're moving on to means now. This book does both of them in the same chapter. And we talked about all of these will be t-tests. The standard deviation that you're going to be given is from the sample. Okay, so test the claim that the mean is less than 200. Mean less than 200, that's your claim. Mean equal to 200. Because it's a mean, we're going to do a t-test, just like when we did on the intervals, a t-test. So we're going to go to our calculator and we're going to enter this information. So let's think of what we have. We know that our sample size is 54. We know that the mean weight from our sample is 183.9, and we know our sample standard deviation is 21.2, and our alpha is 0.10, not 0.01. It's the bottom 10%. So to get to your t-test, you're going to go to stat, you're going to go over to tests, and the t-test is number 2, so it's right at the top. You'll notice this one has 2 options here. Do you have a list of data, or were you given statistics? When you look at this problem, we did not have a list of data. We were given the sample mean and the sample standard deviation. So we're going to move over to statistics, lock it in. Oops. So we have our statistics locked in. Now it's asking for mu sub 0, which it's the mean in HO. Mu equals 200. So 200. The sample mean we wrote down, it was given to us in the problem, 183.9. The standard deviation was 21.2. And the sample size is 54. We're talking about a less than, which was already locked in on my calculator from the previous problem. And we'll go down to calculate. Notice, because it's a t-test, our distribution is not a z. It's not a normal distribution. It's a t-distribution, which we said is very similar. The larger your sample size, the closer it gets to a z. So this is t equals negative 5.58. Sometimes students ask, what if I don't put the t equals? That's okay. You've got that here. I'm reinforcing that. When we do the z, we're going to have a z for our test statistic. When we do a t, we're going to have a t. If you didn't put that, that's okay. I rounded that. Our p-value, again, super tiny. 4.17 times 10 to the negative 7th, or 0.12345, 6, 417. So again, if we were to round this, it's just a little above 0. Like if we had to round it, it would be 0. So it's definitely less than the 0.10, which means we reject the p-value. P-value is less than alpha. So that means we reject HO. We're rejecting that, which means we're supporting our claim. And I realized when I made up the key for this that I have a lot that support the claim, and that's not necessarily the case. If it ends up that you don't support the claim or that you reject or don't reject, don't worry about that part. The results are what the results are. So it's supporting the claim that the mean weight is less than 200 pounds. Something else that bothers me though with this problem, they put men and women all together, and the weights of men and women are usually pretty different. So I think it would make more sense if we were looking at this study to separate it based on gender. Okay. So we're back. I know there's a lot of back and forth with me wanting to show you the calculator, but since it's the first time we've done the hypothesis testing, I want to make sure you know how to enter it in the calculator. In some ways, I almost feel like it works better with the remote learning as far as using the calculator, because you can go back and look at how we entered these problems. And that does tend to be an area students have trouble with. Okay, next problem, kind of appropriate for Halloween. A random sample of 100 pumpkins is obtained, and the mean circumference, the measurement all the way around the pumpkin, is found to be 40.5 centimeters. Assuming that the sample standard deviation is 1.6 centimeters, use a 0.05 significance level to test the claim that the mean circumference of all pumpkins is equal to 39.9. So I see the word mean in here and equal to. So that tells me my claim is going to go in the null hypothesis. And that's the first one we've had that's been like that in this session. The mean is equal to 39.9. We need to put the complement down here. So if it's not equal, it would go like that. And this, if we think about our critical regions, is going to be a two-tailed test. The calculator will take care of that for us, which is nice. When we choose the symbol not equal, it factors that in. So we have one mean. We're going to do a t-test. Go over to the calculator. So looking at this problem, we know we're doing a t-test again. We'll go to stat, go over to tests, t-test. Again, did we have a list of data? No, that'll be our next example. So we have statistics, which should be locked in. Our H sub O, our null, has a mean of 39.9. So this amount would be 39.9. The sample mean was given to us in the problem, and the mean circumference is 40.5. Let me go back there. Sorry about that, guys. T-tests, there we go. So statistics, 39.9. The mean is 40.5. So sometimes students say, well, you can see it's different than 39. We want to check, is it significantly different? That's what a test of significance does. It can't just be a little bit different, it has to be significantly different. The sample standard deviation is 1.6. Sample size, 100. And this one is a not equal, so it's the first one we've had like that. So lock that guy in. So our test statistic is 3.75. And our p-value, 2.98. And again, don't leave it as that. It's times 10 to the negative fourth. This is a probability. So this is 0.000298. Pretty tiny. Our level of significance in this one is a 0.05. So this value is less than 0.05. So again, we're going to reject our null hypothesis. We're rejecting our null hypothesis. What may make this one a little different is the claim was in the null hypothesis. So when we look at the little table to write our conclusions, it's going to say there is evidence to warrant rejection of the claim. We can't support our claim when it's up here. We can just reject or fail to reject. So we'll say there is sufficient, I'll abbreviate, evidence to warrant rejection of the claim that the mean circumference is equal to 39.9. And someone asked me if it's okay to put the symbol in there. It's okay to put the symbol in there. Sometimes if you write it out in words, though, it helps you understand what the conclusion was better. And if there's a question, you're able to address the question. It becomes a little more clear. Okay, let's go back for our last example. I know this has been a longer session. We're almost there. So I filled in the little spots there if you want to make sure you have it on your notes sheet as well. And we're going to look at this last one, which when you look at this, you'll see right here, you have a list of data. What do you think you're going to need to do with that list? Yes. So we're going to need to put that into the list of our calculator, one of the lists. And it doesn't matter which list you choose, but go ahead and maybe start putting that in. So it says when 14 different second-year medical students at Bellevue Hospital measured the systolic blood pressure of the same person. So here's what I want you to think about. It's one person sitting there, 14 different students take their blood pressure. They obtained the results listed below. Oh, this should say sample, not population, because we're not doing that type. So assuming that the sample student, okay. So we're not going to use that part. We're going to use a 0.05 significance level, and we're going to test the claim. Test the claim that the mean blood pressure is less than 140 millimeters of mercury. I think that's what that is. Hypertension is defined to be a blood pressure level that is too high because it is 140 millimeters of mercury or greater. Based on the hypothesis test results, can it be safely concluded that the person does not have hypertension? So we're going to have a question when we're done with this one. So we're going to have to think about our results similar to the confidence intervals where you got your confidence interval first, then you answer the question. So we're going to do the hypothesis test first, and then we're going to answer the question. And again, this part here about the population standard deviation, this book doesn't emphasize the z-tests, which are when you know the population standard deviation. And I actually like that because it's very seldom that that happens. I just forgot to adjust this. So we're just taking that part out. So we know our alpha is 0.05. Let's write our hypothesis statement. Test the claim that the mean blood pressure level is less than 140. The mean is less than 140. That's our claim. So that would mean up here, we would put the equals. Really, though, it's greater than or equal. It's the complement of that. And notice the greater than or equal comes into the question. We have a single mean, which is a t-test. And now we're going to need to go to the calculator to do the t-test. This is the first one that has had data. I want you to see in my calculator, I entered the data before I recorded just to save us some time. So our list of data here has already been entered, and hopefully you have it entered in your calculator as well. And then I just carried over what we had already done as far as our hypothesis statements. We're doing a t-test. So we'll go to stat, we'll go over to tests, and when we choose our t-test, this time, you were probably looking like this before. This time, we want to choose data because we have a list of data that we want the calculator to analyze. What's nice about this, we can just ask the calculator to grab the data from list 1. I've had students in the past that want to find the mean and the sample standard deviation from the list using one var stats and then put them in here. It's faster and it's easier to do it this way. And it also will carry through all those different decimal places or all the different significant figures. So the data is what we already entered. The mu sub 0 is our 140. Oops. There we go. My data is in list 1. You put whatever list you use to enter your data. And the frequency is always 1. I'm going to write that down to just make it stand out. Frequency is always 1. We're not having any of those data values occur more than once. Now we're going to choose our symbol, which needs to be a less than symbol. Lock it in. And we're going to calculate. So we get our test statistic is negative, and actually it's a t, negative 2.51. And then our p-value is the second thing there. In this case, it's the 0.0129. Actually, we should do 30 then, right? 0.0130. Okay. If you want to put the 0 in front, that's fine. Remember, we talked about medical field. You want that for sure. Math-wise, for me, it doesn't matter. Now, our alpha, our level of significance is 0.05. So we have this 0.0130 and this 0.05. So this is definitely less. So we're going to reject. Now, let me show you something. Sometimes students have a hard time with this comparison. There are 4 digits here. If we want to make 4 digits here, you can see 130 is less than 500 if you take the decimal out. So if you have a hard time with that, that's a little trick. Rejecting HO, you're going to get rid of that. So it looks like it supports our claim. Supports the claim that the mean blood pressure was less than 140 millimeters of mercury. Okay. So a couple of things I want to talk about while I have this here, and then we're going to go back to the sheet and answer the question. We had a p-value of 0.0130. And we were talking about a less than, so we were talking about our critical region being in the lowest 5%. That was our alpha. So our critical region here, lowest 5%. And our p-value came out to be the 0.0130. So if I were to think about that, it's, you know, like down in here. It's contained within that 5%. What if I had a different alpha, a different level of significance? And we talked about medical field, we usually choose 0.01. So I'm going to say, what if alpha was 0.01? Well, if we compare our 0.0130 to a 0.01, that's bigger. So we would get a different decision. So the level of significance can make a big difference as far as your conclusion. If we had chosen 0.01 for a level of significance, we would have had failed to reject and we would not have supported the claim. So I just want you to start to see how that level of significance can impact things. Okay, so I want to go back to the notes sheet. Promise, this is the last time. And we're going to answer the question. And you might think about this a little bit as we answer the question. So you can see that I filled in the values that we came up with, our test statistic and our p-value and our conclusion. This one also has a question though. The question says, can it be safely concluded that the person does not have hypertension? Okay. So remember they said hypertension meant that your blood pressure is too high because it's 140 or greater. Okay. Well, we just found that we supported the claim that the mean is less than 140. So initially you might feel like, okay, yeah, it's less than 140. This word safely is important, and there's a couple other things that are important. We found that we supported our claim, but we were at this 0.05 level of significance. And if we're talking about someone's health, we talked about the fact that for medical, we really should use a stricter level of significance. So we want to be more careful with our results. We want to be more confident. And you think about like a 0.01 and a 99% confidence level, they're connected. So we really want to be super sure. So as far as being safely concluded, I would say no. Here's another thing you might look at. This is the same person getting their blood pressure taken over and over, which I would think maybe your blood pressure would get a little higher by the time you got to the 10th or 11th or 12th person doing it. But if I look at some of these values, let's look at how many, this one's over, this one's over, this one's over. So that might be cause for concern as well. This one's equal. This one's equal. That might be some cause for concern as well because we're looking at an average. So the higher values and the lower values are averaging each other out. The higher and the lower are meeting in the middle. This combined with the fact that some of those individual values are pretty high, I would say, can it safely be concluded? I would say no, cannot be safely concluded. It doesn't ask why, but let's answer why. This word safely is what gets me there. I would say level of significance should be more extreme. Or you could say lower because it would be 1% instead of 5%.